This conference will now be recorded.
Good morning. Thank you for joining me. So we have completed the regression, and we are moving on to the next part of the regression things. So we'll have to discuss and complete the rest of the ideas as well. Okay. So first thing I want to highlight here is data science is not just a predefined or structured course. It's evolving, and when I started as a machine learning engineer, I came to know very great things about it and started working on those areas. And now, if I look back, what I have worked on is only a small part of the whole machine learning. And that's how I have elaborated this course so well, covering each and every small thing. Now, what happens is tomorrow, this week, by today, we'll be completing the training models, and next week we'll be completing the support vector machines. After that we'll be completing the TensorFlow. Okay, with that the first batch is completed, provided I have 6 use cases which I'll give to you. If you do that 6 use cases perfectly, every instruction in that use case is very much clearly explained. You have a question and you can approach the answer to that question precisely. Okay, that you need to do that very importantly. If you do that, then you can go ahead and handle any real-time project. I have planned it that way, so you will be in a position to understand things precisely if you complete the use case now, the 6 use cases. Okay, perfect. So that's all about it. So let's complete this one today, and we'll start with the new topics from tomorrow. Okay. Once again, I would sincerely appreciate all your patience, your courage, and your hope for being with me, traveling all the while from Feb 22nd or 23rd, I believe we started it. So it's a long journey, but thank you so much for part of this. Now, ridge regression, I think this I explained yesterday, right? Yeah, lasso also explained. Yeah, I think I explained this point, the lasso regression. Okay. We just spoke about lasso regression and then stopped it there. Okay, so lasso regression is nothing but least absolute shrinkage and selection operation regression. Now we were talking about different type of models and how we train the model and what is the important features, attributes, and what contributes towards the greatness of that model. Putting that points in one roof, what makes the ridge regression so important? The regularization term is added to the cost function in ridge regression, and in lasso regression also that is happening in the same way. Now, very simple. The regularization term is added to the cost function. Now, what the hell is this regularization? What the hell is this normalization? And what the hell is this cost function? These questions you will only be able to answer to your subconscious mind whenever you raise the question is you need to familiarize yourself always. You need to always answer yourself. Basically, I repeat that yesterday also I told you, I would like to repeat it again. Regularization is nothing but it is the process of adding some more information in order. When I say in order, for example, if you have an vector which is not structured or not organized, you're slicing and dicing a vector. So such process, you're adding more information in order to, if you wanted to solve a problem or prevent the overfitting, that is called regularization. Now, lasso regression, ridge regression, and the softmax regression came into picture because they are regularization terms of linear regression. Like that, when you talk to any learning model or algorithm to that matter, you need to know if it is overfitting, how can I regularize it? The regularization term is nothing but how are you solving the overfitting problem. Now, optimization problems can also be solved with the regularization. Very simple. Now go back and question yourself. What is the cost function? What is the difference between normalization and regularization? Now, you understood regularization and you need to understand the cost function. And the way how I remember cost function is, it is all used to estimate how badly models are performing. Now, there are two things here. First term, what did I use? I used the term called regularization. Now, what am I saying? In ridge regression, the regularization term is added to the cost function. Regularization is about dealing the overfitting, and the cost function is about dealing how badly your model is performing. Okay. Now, when I say the regularization term is added to the cost function, then it means I'm going in a right direction towards getting the best predictions and best accuracy. Because regularization is dealing with cost function. When regularization is added to the cost function, regularization is all about overfitting, and the cost function is all about. I'm asking a question. Cost function is all about how badly your model is working. So that is regularization. Now all the slides in this section is nothing but you are trying to deal with an overfitting problem, and you are also trying to deal with a case where a model is performing badly. Now but it uses the L1 form of the weight vector instead of half of the square of L2 norm. Again, if you have read or understood SLS class, L1 is all about mean absolute error, L2 is all about RM square error, and weights here, what it is saying is, it is using the L1 form of weight vector instead of half the square of L2 norm. So I don't care what it is using, but all I care is I need to understand the concept of lateral regression. Now, let me show you the differences between lateral regression. Now, if you see the plain regression model, you have an alpha equal to 0, alpha equal to 0.1, and alpha equal to 1. Okay, the red dotted line is alpha equal to 1, a straight dotted line, a green line equal to alpha equal to 0.1, and a green line, dotted blue line is alpha 0.1, and a green line is alpha equal to 0. Okay, guys, hope you are able to see my screen. I'm writing something. Perfect, you're able to see it. 0, 0.1, and 1. The green color, the green is 0, which is this one. The blue is 0.1, which is this one, and the dotted red is 1. Now, how is it looking linear regression? It is nearly there, but how is it looking in the polynomial regression? See how bumpy and how curvy it went. That is one area, and this is one area. However, this one is always same in the linear regression and also in the polynomial regression. Okay. Now here alpha equal to 1 red line is same in both the cases. This kind of observations are very important. This behavioral change looks this way only because of the way the normalization, the cost function works in the background. Take down a paper, write the differences between all the models, stick it on your wall, you are done. You will be able to answer that question whenever you need. You will have to do this kind of homework. You will have to do this kind of homework. Only then you will be mastered in machine learning. Guys, trust me, again, this question and this type of normalizations, regularizations, cost functions have been asked in every interview for me. And yesterday also when I attended an interview, they asked me, when do you prefer linear regression? When do you prefer logistic regression? Why do you think linear regression is only correct for this case? And how do you deal with the errors in the linear regression? They are only asking about how. What have you done? What have you done? How did you solve the problem? You will understand these things only if you maintain a notes of yourself, understanding the core concept and linking the gaps. If you don't do that, then you're not doing any favor for yourself. I'm serious about it. Take it seriously. Okay, we are good till this point. Hope everything is clear. Hope you all understood what I mean by a lasso regression. Now, let me erase all the drawings. Okay, let me go back to the pointer. Cool. 87 slide. Now, I wanted to show you something. Lasso regression on some linear data using different value. Okay, here in this diagram, I have shown you with alpha equal to 0, 0.1 and 1. Now I wanted to show you something pretty different. Okay, if you see on my right side, simple, go to scikit-learn. In scikit-learn library, you have a class called linear underscore model. In that, import lasso, take a variable, assign the variable to your linear regression model, a lasso regression, and fit it to your features and labels, and then get the predictions of 1.5. The reason why I have taken 1.5 is there's a different value I have taken here. Okay, now I got a value array of 8.315. This array of 8.315 is a random number which I have taken, and for that random number, this is the output. Makes sense. Now, 1 minute. This shouldn't look like this. It should go like this. Okay. Now, an important characteristic feature of lasso regression is it completely eliminates the weights of least important features and sets them to zero. Very, very important. This is what makes it so good. Okay, try to understand. The important characteristic feature of lasso regression is it completely eliminates the weights of least important features. Again, least important features means think practically. You have been given 10 columns. For sure, all the 10 columns will not help you in the model prediction. All you need is the best combination. That's the reason we call best important features or best combination attributes or experimenting with attribute combinations, which means you have various scikit-learn libraries which you can import to use. Give me the top five features which will help in my prediction, because you know what you're expecting, and for your expectations to be accurate and work well, you just have to do one thing: select the models. Now, the important advantage of this lasso regression is it will eliminate the features that are least important and sets them to zero. In that way, it has reduced one step of work for you. Happy. Now, lasso regression automatically performs future selection. When I say future selection, again, future selection is all about the above point I covered, the important features, i.e., model with few non-zero feature weights. The least important features are ignored and they are added a value 0. Now, the dashed line green with alpha equal to 10, this one. 1 minute, guys. 1 minute. When I say this one, that is this one, 1e minus 0.7. Okay. Now here, the dashed green line with alpha equal to 10 to 0, that's exponential form. So don't worry. That's just a value we give to the learning curve or cost function. The right hand side point looks quadratic, almost linear, because if you see here, it is quadratic, right? Now, all the weights for the high degree polynomial features are equal to 0. Okay. All the weights for high degree polynomial features. Now, this is the normal linear regression and this is the polynomial regression. That's what I have shown you in the previous diagram also. When I say all the weights for high degree polynomial features are equal to 0, this green dotted, the dashed green line is looking like this and came up like this because it has considered all other non-important irrelevant features weights as 0, and it brought it like this. That's all it is. This is the way you need to understand. Every model will have a diagram, and that diagrammatic representation and how you can link what you understood that diagram is very, very important. Okay, hope you understood what I'm saying. Hope you clear. Very simple. Here we are trying to understand what is the advantage of lasso regression, what is the beauty in it. Lasso regression is all about it deals efficiently with the important relevant features, and it ignores the irrelevant non-important features. It adds a value 0 to it. Okay, now in that way the predicted line or curve looks quadratic and almost linear. That's all I can say. Okay, erase all the drawings, go back to the pointer. Now go to 88th slide. Now we are talking about elastic net. Now we completed the lasso regression, we completed the ridge regression, we are talking about the elastic net. As the name itself, it is elastic. When I say elastic, it can bound to left, it can bound to right, and if you put strict uh, uh, if you put a strict what I can say, if you put strict surveillance on it, it can stay in middle. Oh, so the elastic net is a middle ground. It's between the ridge regression and lasso regression. The regularization term is nothing but simple mix of both ridge and lasso regularization terms. Now, to understand this one, you need to go back and memorize what you have discussed in the ridge regression and lasso regression. Let me go back a minute. Okay, this is the ridge regression. In the ridge regression, what we discussed is data is first expanded using polynomial features, then they are scaled using standard scalar. Finally, the ridge models are applied to resulting features. Now, polynomial regression with ridge regularization will have flatter, less extreme, more reasonable predictions. This reduces the model's variance but increases the bias. Okay, now this is not important. This is not important. Yeah, this is important. See, what we spoke about ridge regression is this ridge regression will force the learning algorithm not only fit the data but also keep the model's weights as small as possible. When I say model's weights, it is not making the most important relevant features and ignoring the relevant features and adding zero weights. It is actually putting all the weights as small as possible. Now the regularization term is added to the cost function. This sentence is being represented there as well. So regularization is all about how we are dealing with overfitting. The cost function is about how we are dealing, how bad your model is performing. So these are all the same terms you're working together. Now, again, regularization, if you see here, note that the regularization term should only be added to cost function during the training only. Once the model is trained, we evaluate the model's performance using the unregularized performance version. This understanding what you have in ridge regression and this understanding what you have in lasso regression is nothing but both are combined in the elastic net. Okay, now in elastic net is nothing but a simple mix of both ridge regression and lasso regression. Now the elastic net is considered like we considered alpha equal to 0, alpha equal to 1, alpha equal to 1.5. Here we say r equal to 0, r equal to 1. Now look at the diagram and link that concept to the explanation. Let me take an pen here again. Now when r equal to 0, now this is the elastic net cost function. If r equal to 0, the elastic net is equal to ridge regression. Okay, when r equal to 1, elastic net is equal to lasso regression, this one. Okay, and when r is not equal to 0 and when r is not equal to 1, this is the lasso regression plus this is the ridge regression. So elastic net is nothing but based upon the r value. At times it acts as ridge, at times it acts as lasso, and if you are at the middle ground, then it is the combination of simple mix of both ridge regression and lasso regression. As simple as it is, you do not have to worry about it. Do not even mind or care to remember the formulas. You can never do that. And if you try to do that, you're simply breaking your head, because as I told you, as I repeatedly keep telling you, the formulas are however being covered and interpreted with the Python libraries. Okay, hope that makes sense. Now let me move on to next slide. Hope it is making sense, and I believe you guys are able to connect the dots properly. Now go back to the pointer, erase all the drawings, go back to the pointer. Okay, now 89. Perfect. If you have to implement how to use, when we should use linear regression, when we use digital regression, when we use lasso regression, and when to use elastic net. Next slide, we are going to talk in detail when we should use which one. This is very, very important. We have reached this point and we understood. Again, guys, as a human beings, it's highly impossible for us to keep a track of all the previous sessions and what we have understood. So kindly take down a book, have a dedicated book for the whole notes, write down the date, write down the concept, make a note of what to understand. Go to next video, make a date, keep the topic heading, make a note of what you understood. At the end, relate the concepts of last recording and this recording. Like that, if you just spend around 1 hour max, I don't want you to listen to the recordings. I want you to just watch the slides. Just watch the slides, because practical implementation I have implemented practically and attached the screenshots for every one of you. Again, in this training models, we have not did any use case. We have just took numpy random numbers and worked on it. So the result will change for you and for me. Don't worry. If you go to the top of the slides, in the first slide, I implemented numpy random.rand number 1 to 100, which means every time you run the model, the random numbers will be initiated. Your model will be running on those random numbers. So don't worry if the output for you and for me is changing. Okay. Now, but you need to make a note of the whole process and how it's running. That's very important. Okay. Now, to implement the elastic net, simply from scikit-learn you have a linear model class. In that you have a subclass elastic net. Import it. The L1 ratio is nothing but it is correspond to the mix ratio R. When I say mix ratio R, it is R equal to 0, R equal to 1. Is here I am taking 0.5. Okay, random state equal to 42, alpha equal to 0.1. When I say alpha equal to 0.1, that's a cost function. You know, here you're mixing up the cost function with the regularization term. So after that, you're fitting your elastic net to your features and then the labels, and you're getting the predictions for 1.5. That's all it is in this one. Now let's jump to the important point: how, why, when we should use linear regression, lasso regression, ridge regression, and elastic net regression. Okay. Now this is very important. I would request you all to take a photo of this immediately, right now. Quick, take a photo of this. Support vector machines is going to be much fun. TensorFlow is all about GPUs. GPUs is like how I'm not sure if you guys are aware of Spark in-memory processing, RDD processing. Like that, you have TensorFlow. Once you finish the TensorFlow, you are completely a real-time data scientist. Again, when I say data scientist, when I say artificial intelligence, when I say ML, all are same. Do not worry. And we are also going to build a use case for NLP, natural linguistic processing. I already started working on it. I'll add you all in that video. But guys, it's a continuous journey. The amount of time you invest on it will definitely pay you back. But investment of time is very important. Let me also done. Okay, I hope everybody have taken a copy of this. Let me see how many of you have done. Perfect. That's good, guys. That's good. Now, first understand when you shouldn't do a mistake. So we should avoid using plain linear regression. Okay, when you have preferably to have at least a little bit of regularization. Okay, linear regression is always preferable to have at least a little bit of regularization. Okay, if you have too much of regularization, then you can use linear regression. If you have a little of regularization, don't use linear regression. Ridge regression is good by default, but if you think only few features are useful, then you should go with lasso or elastic net, as they reduce the useless features weights to zero, which I explained you very nicely. In general, elastic net is preferred over lasso. Why? Since lasso may behave erratically. When I say erratically, it depends upon how many features you have. When I say how many features you have, how many number of features you have. E is greater than the number of instances training when several features are strongly correlated. So what I can make out of this slide is all the models behave in the same way. But when you're dealing with the features, and if you can make a tight coupling of the important features and their weights, the approach changes. The regularization comes low. Linear regression must be used when you have so much of regularization. Okay. If you have a little bit of regularization, you don't use it. Okay. But you always linear regression is always at least preferred. Now, you know elastic net is combination of lasso and ridge. I also told you what happens if your r equal to 0 and r equal to 1. Again, r equal to 0, r equal to 1 is dependent on how your features are tightly correlated. Okay, that's all you need to understand. Hope you got the point clearly. Let me move on to next slide. Here, early stopping. What is early stopping? Why is it so important? Look at the diagram, guys. At one point, at one point, you know, it came down. Look at the highlighted bit. It was so bumpy and curvy from 3.5, and when it reached to 220 or 230, it landed, it touched the ground, and then started going a bit up. What is this? What is this? Can anyone guess? Can anyone guess what it is? No guess? Okay, don't worry. That explained in the right side of the slide. Now, first of all, I want to explain you something. In machine learning, the way the model trained is called iterations, batch sizes, and epoch. Epoch, E-P-O-C-H. I repeat, the epoch, batch sizes, and iterations are synonyms. Okay, when I say synonyms, these are the terms that are quite often used in machine learning because this epoch is nothing but a representation of a data set from which machine is going to learn. And when you say machine is learning, it is actually making a lot of feeding the data and learning from the examples iteratively. Okay, now we are talking about the regularization of the linear regression. We are talking about the regularization with cost functions. Now, A different way to regularize iterative learning algorithms, such as gradient descent, is to stop the training as soon as the validation error reaches the minimum. We know that when the validation error is reaching to the minimum, when I say minimum, you have error as 10, again you got error as 8, next one you got error as 6, next you got error as 2, but you will never go to 2, you will never go to 0, you will stop at 2, because you want a minimum validation error, not a zero validation error. Now, the point at which you stop training is called as a early stopping. Now, in this point, this is the early stopping. You can ask me, why not this one till this one? Because it started coming down from here, again it started going up from here. So I'm only concerned about this point. Okay, error was 10 here. It might be 9 here. It might be 8 here. And it might be 2 from here to here. Okay, now this is the best model. Any model you're talking, always visualize with this kind of diagrams. Okay, look at the training set, look at the validation set, how the training set is behaving. It went so deep, and the validation was not that deep, it was quite up when compared to the training set. Now, epoch is nothing but your batch size, your instances, or your iterations. Now, when the epoch is increasing, means when the iterations are increasing, when the batches are increasing, its prediction errors, which is called as root mean square error on the training set, goes down. That we know. So the prediction error on the validation set also goes down. Perfect. After a while, the validation error starts increasing. Again, guys, understand the question, understand the point carefully here. When the epoch is increasing, means when you are training your model with more instances, basically the error should come down. But when you are dealing with the learning curves or early stopping, if at all your prediction error goes down, it also goes down one validation set. And after a while, it starts increasing. Look at the diagram. That's what I've explained in the diagram. Erase all the drawings. I'll take a different pen now. Choose a pen, brown color. Now, see for example, here the validation is again increasing. Okay, it's getting down from here. It got down from here to here. It was grounded and touched the ground. That's the reason I said best model. When at what rate I reached here is the best model with best hyperparameters. Okay, now when the validation set started increasing again, the model has to, this indicates that the model has started to overfit the training data. Again, overfitting the training data is dealing with regularization, dealing with the cost functions. Okay, this is called the early stopping. What is the impact of this early stopping is what we need to be clear about. Erase all the drawings, guys. You need to stop me if you're not aware, if you're not clear. Okay, the session is recorded, the screen is shared. Good. 92. Now I'll give you a tip. With early stopping, we just stop training as soon as the validation error reaches the minimum. Okay, when I say minimum, the smart guy will stop the training abruptly when he reaches this point. Okay, till this point, stop at this point. That is very important. Please, 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 Fozio, register this kind of diagrams on your mind, because all these days you are from different background and you are trying to take something new there is a 200% possibility that things tend to confuse you and you may overassume or you may think less about a concept. For that reason, every diagram in this one, visualize, okay, this guy is telling like this. Oh, the concept is looking like this. So I have to focus on this one. Now, when somebody asks you about epoch or early stopping, you'll clearly say, boss, at times your validation error comes down, it reaches to a good stage, again the validation error goes up, and at the value where your validation error came down and sat there for quite some time and then moved up, that is the early stopping rate, which is called best model. That's all you need to know. Look at the diagram. The diagram actually makes sense, more sense than what I am talking theoretically. Okay, that's very important. Now, okay, let me erase the drawing. Look at the tip. The tip is also very important. With early stopping, we just stop training as soon as the validation error reaches minimum. That's the thumb rule. Now, in the previous example of batch gradient descent, the curve was smooth. That is why we could locate the minimum easily. With scotatic and mini batch gradient descent, curves are not smooth, and it may be hard to know whether we have reached minimum or not. Imagine the example of you are on the top of the mountain and you are stuck in the fog and you need to come down to the bottom. How do you go? What is the learning rate? And how you fall down there and how you control your steps in that concept is nothing but the early stopping in this concept. Everything is linked, guys. Everything is linked. If you understand one model perfectly with the end-to-end flow, you can implement all the models with the same understanding with 200% accuracy. I'm saying 200% accuracy. Things are so simple and so straight. Don't complicate it. At least one model, you learn it perfectly, the whole flow, how to deal with it, how to deal with the normalization of the model, how to deal the regularization of that model, how to deal with the cost function of that model, how to deal the learning rate of that model, how to deal with early stopping of that model, and how to get the best predictions, how to do the validation of that model. If you understand one model perfectly, it's same for all other models. Okay. Now, one solution is to stop only after the validation error. Means when the validation error reach minimum, stop there. Has been above minimum for some time. If it is reaching above minimum slowly, then you need to be very careful at that point. Roll back the model parameters to that point where it sit at the minimum error for quite some time, where the validation error was at a minimum. These are the important tips. Again, what we discussed in the previous slide is again discussed in this slide, but we have compared how things work in scotatic gradient descent, mini batch gradient descent, and the scotatic descent and mini batch gradient descent. That's all it is. Okay. This is how you need to understand and work on early stopping as well. Perfect. Making sense. Go back to the pointer. Now, the next slide is logistic regression. Very, very important. So, what do you understand about logistic regression? How to implement the logistic regression? The logistic regression is a binary classifier. Okay. When I say binary classifier, it's not zeros or ones. The classifier that classifies us with the binary representation. Now, more importantly, people tend to confuse a lot between logistic regression and linear regression. And the differences between logistic regression and linear regression is asked in almost all the interviews. Almost all the interviews. Trust me, that's very, very important. You need to know the differences between logistic regression and linear regression. Okay. All I can say is logistic is all about a classification algorithm. It takes some observations, and from the observations it creates a set of classes. When I say class, apple is one class, orange is one class, banana is one class. Okay. Now the examples it has taken in apple, banana and orange, it will try to implement that process throughout the journey of the iterations. For example, let's take the email spamming. Or let's take an online transactions. Okay, this type of logistic regressions is transforming some outputs for you, and they are using the logistic sigmoid functions using a probability value. Okay, what the points what I have told you is from my understanding how I remembered the things. It may not go well with you, so I'll go with the slides. Before I go with the slides, I want to understand what do I answer when people ask me about the logistic regression. I just say one thing I remember in logistic regression. See, simple boss, every person has their own way of memorizing things. That 1 second, guys, give me 1 second. I may say A to B, you may say B to A, but the wording and the terminology is very important. So for me, all I remember is logistic regression is using a sigmoid functions. Within the sigmoid functions, it will return the probability value. Okay, and logistic regression, uh, logistic regression will take the observations and it will create the set of classes. When I say set of classes, the set of classes is nothing but apple, banana, orange, or this email is spam, that is one class. This email is not spam, that is another class. Now, if it is fraud, it is fraud. If it is not fraud, it is not fraud. That's all it is. That is logistic regression. Now, let's read to the slides and understand better. Logistic regression is the binary classification. Okay. Again, you have you have multilinear functions also, but I will not talk about it now. We'll do it in the use case. Now, logistic regression is a binary classifier. It is used to estimate the probability. When I say probability, an instance that belong to a particular class. For example, I gave you banana, orange, and apple, or banana, apple, and orange. When I gave you banana, apple, and orange, you are able to classify it properly depending upon the length of the fruit, breadth of the fruit, or color of the fruit, whatever it is. Is it an apple? Yes. If it's not an apple, it must be an orange or a banana. Is it an orange? Yes, it's an orange. If it is not an orange, it must be an apple or banana. Is it a banana? Yes, it's a banana. If it is not banana, it must be an apple or an orange. This is how the logistic regression works. You have positives and negative class. Example, what is the probability that my email is spam? That is the probability ratio. Now, if the estimated probability is greater than 50%, then the instance belong to class positive. Then the positive class is labeled as 1. I am very bad here. I should have done this way. Yeah. Now, 1 minute, guys. Let me save this one. Again, this one also. I have not done the. Okay. So now, estimated probability, if it is greater than 50%, then the instance belongs to the class positive. If the instance belongs to class negative, then that is labeled as 0. That's all about logistic regression. Again, logistic regression you understood carefully. Now, if I ask you about linear regression, again you'll have to go and understand reading it. Don't do that. Have a pictorial representation of all the models. Linear regression is nothing but it is a supervised learning. It is performing a regression task for you, and basically it has a relationship based upon the independent variables, and it also have a different line of formulas. For example, y equal to mx plus b, or where you have y as predictions, x as an threshold value, or b as something. Okay, maintain a book for yourself and understand the differences, and just just have a flow of things. That's very important. Don't confuse between linear regression and logistic regression. Logistic regression is a binary classifier. Logistic regression is used to detect yes or no. If yes, that is true. If no, that is false. S will have one value. No will have a zero value, and it estimates the probability. That's all I can say. Linear regression is not like that. Linear regression is a supervised machine learning, and linear is performing a regression task. What is the word itself says the regression task. Regression is nothing but it is targeting the predictions based on the independent variables. When I say independent variables, what are those independent variables? Those independent variables are your futures. So what do you understand by that? You understood that the prediction value is based upon the futures. Now, how much is the relationship of your independent variables versus your target? Can you plot a diagram? Can you relate to the diagram? That is linear regression. Simple it is. Simple. Clear, guys? Yesterday also I've taken one interview, and in that also he asked me very clearly, Amarnath, can you explain the difference between linear regression and logistic regression? On top of it, what is the formula you have in linear regression? What is the line of graph in the linear regression, and what is the probability prediction in logistic regression? He also asked me the formula of linear regression, which is nothing but theta of zero and all. I said, boss, let me be honest with you. The moment I started data science journey, I never remembered any formulas. I know how each formula works. I know the regularization, the normalization, the cost functions, the learning rates, and the easy early learning stoppings of all the models. But don't ask me the diagrams. Don't ask me the formulas. I don't remember it. And if you remember it, then I learn it from you. That's what I told him. Formulas you need not have to remember, but remember what are the parameters that can tweak the model's performance. That's important. Now, 95th slide. Look at this diagram, guys. Estimating probabilities. Now, what is linear regression, guys? What is logistic regression? It's all about binary classification. It's all about finding yes or no. It's all about estimating the probability. Is the probability of fruit to be apple? Yes, it is. If not, what? That is what it is. Now, I told you very clearly, the logistic regression uses the sigmoid function with the probabilities. So you need to understand what is sigmoid function and how the probability works in the sigmoid function. Okay. Now, let me take a few minutes and explain you that. What is the time? 6. Enough. We have enough time. Don't worry. Just like the linear regression model, a logistic regression model computes the weighted sum of the input features plus the bias term. So now, when I say y equal to mx plus c, y is your predictions, m is number of instances, and b is your bias term, and x is your weighted sum. Okay, but unlike the linear regression model, logistic regression model outputs the logistic of the result. Logistics of the result means yes or no. That's it. Now, logistic regression model estimated probability. Look at the diagram, and that diagram will explain you what I mean. Okay, if this p it's 6 hours. If this p cap is less than 0.5, then the result is 0. Means that's a negative class. If p cap is greater than 0.5, 50%, then it is 1 true class. Okay. If an apple is apple, that is 50% more. It classified the estimated probability is more than 50%. That's why it is apple. If estimated probability less than 50, that is false, which is 0. Okay. That's the beauty of this. And again, as I told you earlier, do not even worry to understand this formula, but just remember this thing. This is nothing but the sigmoid function. Logistic regression is working on sigmoid function with estimated probabilities. Logistic regression is working on sigmoid function with estimated probabilities. Logistic regression is working on sigmoid function with estimated probabilities. If this sentence is heard from you, then the interviewer will be very happy. Linear regression is the supervised machine learning. Linear regression is all about how you get the predicted value based upon the independent variables versus predictions. How you create a line of graph explaining the relationship between your predicted values and the independent variables. That's all. Just make one line that is easy for you to adapt and explain. That's all I would say. Now, look at the diagram here. This diagram is nothing but it is explaining this one here. Okay. If you see, this is 0, this is 0.5. If it is more than 0.5, this is positive class. If it is less than 0.5, it is negative class. If you observe carefully, this is something looking like an ROC curve trade-off, bias variance trade-off. It looks like that, but not exactly that. So what do you understand by this? Every model has same kind of approach, but the terms within it will vary, and you need to remember those terms. That's all. Perfect. Let me erase all the drawings. Let me go back to the pointer. Now, look at this diagram. And in this diagram, what happens if your estimated probability is less than 0.5 when t is less than 0? And what happens if your estimated probability is greater than 0.5 when t is greater than 0? So, the logistic regression model predicts 1 if theta t dot x, again capital X is a matrix, if theta t is nothing but transpose of t. When I say transpose of t, your vector is transposed into a matrix of rows converted to columns. When that is positive, it is 1. When it is negative, it is 0. Okay, that's all you need to understand. Don't worry, don't break your head. This is about logistic regression. Now, training and cost function. So you talked a lot about normalization, regularizations, cost functions, early stopping, learning rates, blah blah blah. Like that, the logistic regression also has a training and cost function. How do you deal with it? Let's understand how to train a logistic regression model. The objective of this training is to set the parameter vector theta so the model estimates. Very good. I understand that carefully. High probabilities for positive instances y equal to 1 and low probabilities for negative instances y equal to 0. Super. Note that in this case of classification, y can only have two values. That can be 0 or 1. Look at the diagram, guys. This is your 0. This is your 1. Okay. Now this is y log of p cap. This is y minus log 1 minus p cap. In this way, if y equal to 1, it came this way. Positive predictions, no, when a positive probability, y equal to 0, negative probability. Okay, this is simply vice versa into this one. Sorry, like this. Okay, now the cost function of a single training instance is nothing but implemented over here. Y equal to 1 is this one, y equal to 0 is this one. Okay, simple, very simple. If your observations pass in positive class, that will be y1. If you know all are positive, it looks like this. If you know all are negative, it looks like this. As simple as it is. Okay, done and dusted. Good job, everyone. Let's move on to next slide. Now, here, training and cost function continuation. Let's deep dive a bit. Let's deep dive a bit. Okay. Now, this is y equal to 1. This is y equal to 0. This is y equal to 0. Again, this y equal to 0 has a small difference such that the y and x, the point where they started and the one time it took to reach here is also important. Okay, now let me explain it logically so you'll get an understanding of what I mean. If y equal to 1 and p cap equal to 1, both actual and predicted probability are at 1, then cost is equal to 0. Okay, sorry, I pointed a wrong diagram. 1 second, guys, give me 1 second. Let me take a pointer. Let me take a pen now. Now, your y is equal to 1, this one. Your p cap is also equal to 1, this one. Guys, you should ask me a question, what the fuck is this p cap? The p cap is estimated probability. You have to get this question. You guys are not focusing. I'm telling you something very important. Relate, relate, relate. P cap. Amar, you should have asked me what is P cap. P cap is the estimated probability. Okay. Now, if your Y, the predictions is going to be 1, and if your estimated predictions is also going to be 1, then cost is equal to 0. Obviously, because they both are in line. They both know what they are doing. They are at best performance rate. So the cost is 0, which is this rate. Now, if y equal to 1, okay, and p cap equal to 0. Now, when I say y equal to 1 and p cap equal to 0, if it starts at this point. Now, guys, when my p cap is equal to, when p cap equal to 1, it started at this point. It traveled all this way to there. Let me erase the drawing again for you. Now, see here, if my y is equal to 1, p cap equal to 1. When my p cap equal to 1, this is how it looked, and cost is 0. Perfect. Now, when my y is equal to 1, this one, and p cap equal to 0, which is this one. Okay. Now, the predicted probability is different from the actual value. So this is the area where it focuses and says at p cap equal to 0, the cost will be infinity. When I say infinity, you are not sure at which point you should stop, right? And we penalize the algorithm at a very large cost, means we are making it more complex. Likewise, if you take y is equal to 0, and if you take your p cap equal to 1, this one, sorry, if you take y equal to 0 and your p cap equal to 1, then what happens? The predicted probability is different from the actual value. Then the cost will be infinity. Okay. The y cost will be infinity is it keeps on going up, and again we penalize the learning algorithm at very low cost, here at large cost, because your y equal to 1, p cap equal to 0. Y equal to 1 is actual predictions, p cap is the predicted probability or probability predictions. Okay, p cap is probability. When your probability equal to 0 and prediction equal to 1, you are training algorithm at a very large cost. When your prediction is 0 and your probability is 1, then you are training at very low cost, vice versa. Now, if your probability is 0 and your prediction is also 0, when both actual predicted probability are 0, then cost is 0. What can you make out of this diagram and concept? Basically, this one loves this one, this one loves this one. So both the actual and predicted probabilities, when they are same, the cost will be minimal to 0. When the predicted probability and the actual value are totally different, then it causes a problem. You need to decide, are you training the model at large cost or are you training the model at low cost? That's pretty important. Are you all clear with this one? If you are not clear with this one, I'm sure you will mess up in the interviews and the real-time implementation. This is the one that makes the distinguished differences between logistic regression and the way how the predicted probability works. All good, everyone? Everyone, Kavi, is all clear? Kishore? Cool, perfect. I have 15 minutes time. I have to finish. I have 20 minutes time left. I have to finish it in 20 minutes. Give me 1 minute. Pointer. Now, decision boundaries. What are the decision boundaries? How can you make a decision boundaries work for you? Again, guys, when you say the probability of 50% more, you said there's a positive class, you said 1. When you said the decision probability is less than 50% as negative class, that's 1. What is the decision that is making it 50, less than 50, greater than 50? You need to know about it, right? Now, to understand that decision boundaries, let's use an iris dataset to illustrate the logistic regression. This is a famous dataset that contains the sepal and petal length and width of 150 iris flowers of 3 different species. One is Iris setosa, one is Iris versicolor, and one is Iris virginica. Okay, perfect. Let me show you something. This diagram itself tells what exactly we're dealing with. Okay, guys, these are features. What are the features? Your sepal length is one feature, your sepal width is one feature, your petal length is one feature, your petal width is one feature. Got it? Everyone? Guys, please focus if you are feeling drowsy. Please focus if you are not properly focused. This is very important. These are the features. Features can be attributes, features can be measurements, features can be dimensions. Super. Now, class. This is the Setosa breed. This is versicolor breed. This is virginica breed. This is class labels. You are labeling it as banana, you are labeling it as orange, you are labeling it as apple, like that. Now, this is sepal. The whole set is called sepal. The bottom is sepal, the top is petal. Now, do you see here? I'm calling it as petal and I'm calling it as versicle. I'm calling it as sepal. This is Virginica brand. This is Virginica breed. This is Setosa breed. Okay. Now, samples is number of samples. You have 150 records. That is sample. Your features is your columns, and your class is your targets. Your target is nothing but what are you working on? I'm working on fruits. What the hell is fruits? I'm working on apple, banana, and orange. Oh, now I understand what you're working on. That is class. Okay. Again, sepal and petal are not that important, but you need to know and you need to deal with sepals and petals in a proper way. Now, at times, at times, this level of understanding will be more than enough. But if the use case is very complex, you'll have to deep dive into this one and understand the petal, understand the sepal, understand the sigma, all these things. Because your decision boundaries can decide based upon the overall look. But sometimes what happens if it is not able to identify properly? At that time, it will go and check this area also. Do you see? I'm highlighting something. It checks this area also, the center area. To check and distinguish this area, it must know what is that area. That is stigma. It is also an ovary and ovuleus. Okay. This is how the boundary decisions works. This is how the classification works. When it is trying to classify based on the length, breadth of the fruit, if it can classify it properly, it does. If it cannot classify, then it makes a boundary decisions. Okay, this guy gave me a different fruit. This is not in height, so definitely it's not banana. It's not circle. It's definitely not orange. It's not in circle, and the top is not in curvy, so it's not apple. What the hell it is? Okay, is it something other fruit with a round shape? Is it some other fruit with a round shape and curve on the top? Or is it the shape of the fruit has changed? This kind of questions. That is the decision boundaries. Okay. Hope that's making sense, guys. Erase all the drawings. Go back to the pointer. Now here, I have implemented this one. Very simple. Go ahead from scikit-learn, import the datasets. Just say iris equal to dataset.load iris. You'll get the data, you'll get the target names, description, feature names, and file name. So that's a flower you have imported. From that one, if you just say print iris data, print iris features names, there are 150 targets with 50 zeros, 50 ones, and 52s. Okay, so what I am dealing here is I'm talking about this one. 50 zeros, 50 ones. What are these twos? That's a different story. Okay. What does 0 and 2 mean here is what we are going to understand. Okay. Erase all the drawings. Move on to the next slide. Let me move to the pointer. Erase all the drawings. Go back to the pointer. Now look at this. If you look at this diagram carefully, I have put everything nicely. This is target. If you see the description of the iris data set, you have data, you have target names, you have description, you have feature names. Now if you see the feature names, you get the sepal length, sepal width, petal length. And if you talk about iris data, it gives the data like this. This is the matrix again. In this matrix you have sepal length here, you have petal length here, you have sepal width here, you have petal width here. This is a matrix where all your features are sitting. Now if you just check the target, you have zeros, you have ones, you have twos. 0 and 1, you know, if it is 0 that's negative, if it is 1 that's positive, but what the hell is 2, we'll deal with that later. And if you want to check the target names, go and check the target names, you'll get Setosa, Versicolor, Virginica. Okay, this is how you can visualize the data set and get closer to the decision boundaries. Erase all the drawings, go back to the pointer. Okay, now let's build a classifier to detect the iris virginia type based on the petal width feature. Understand, guys, this is one of the use case. Build a classifier to detect a virginica type based on the petal width feature. Okay, to do that one, very simple. Go ahead and load your data and then come up with what is your features, what is your labels. My feature is petal width, which is 3, and my features is X, which is iris with petal width 3, and my target labels is 2, where if iris virginica or L0, and I implemented the logistic regression. From the logistic regression, I said I implemented the random state 42 and I fit the model. Okay, whatever I have done there, it is represent diagram here. You guys have to practice it. Guys have to run through it. Okay, now probability model estimated probabilities. Okay, here also we need to know how the decision boundary works. If you plot a diagram carefully, okay, that diagram will show you how things are working. Okay, now look at the diagram, guys. Understand something. This is the decision boundary exactly. Okay, if it goes in this direction, okay, that is virginica, and if it is going this direction, that is anything other than not iris virginica. For example, if male is spam, all the spam mails comes in this direction, all the non-spam mails comes in this direction. As simple as it is. All the bananas will come here, anything other than banana will come here. That's how the classification works. This is called the estimated probabilities and decision boundaries. In here, what you understand is at 1.6, they have met and came to understanding. This 1.6 is the model estimated probability curve. Okay, now to do the model estimated probability, go ahead and use a linspace and implement the y underscore proba. Again, y underscore proba is nothing but probability, and plot that, and that plot will give you this kind of diagram. You are good to shape and you'll understand what I meant. Okay, hope it is very clear. Very simple. We have been talking about apple, banana, orange. Please apply that logic here. You are good. Okay, the next slide. Model estimated probability continuation. Again, guys, I'm going to make more observations from this one. The petal width of Iris Virginia is represented by triangle. Okay, which is nothing but this bit, this triangles and this triangles. Okay, now ranges from 1.4 to 2.5. Okay, from when I say 1.4 to 2.5, 1 minute guys, where is 1.4 to 2.5? From here 2.5, 1.4 should be somewhere here. Sorry, 1 minute. Come on, yeah, straight line here. So from this point to this point. So this is the highlighted area. This is what you're focused on. Now, the other iris are represented by squares. See, this is a square. This is a square. So your Virginica is represented by triangle here, and your other iris flowers are represented with squares here. These are having a small petal width, that is fine. Having a range from 0.1 centimeter to 8 centimeter. So started from 0.1 here, and the last one is 1.8 till here. Perfect. Ranging, that's fine. Notice there's a bit of overlap. Yes, there is an overlap, that's fine. But how does this classifier predict them? That is the important bit. Okay, now to understand that, we need to complete one more slide. Look at this one. This is more practical. This one, if above 2 centimeters, the classifier is highly confident that the flower is an Aries virginica, as output is high probability to the class. Okay, now 1 minute guys, let me show you practically. Let me take a pen. Above 2 centimeters, okay, in this direction. Now, while below 1 centimeter, it is 1. Okay, now if anything below 1, the classifier is highly confident the flower is not an Iris virginica. If it is above 2 centimeter, it is confident the flower is Iris virginica. Now, here what happens is, as it outputs high probability of not Iris virginica class, there is a decision boundary at 1.6. That decision boundary is nothing but this bit. When you are working with real-time scenarios in business, this is how you need to show the diagram to business. Data science is all about storytelling with data. Data science is all about how we visualize and represent your shitty data into a meaningful business use case. Learn things right now. Understand how things will work. That's very important. Okay, this is nothing but the decision boundary here. Now, where the probability equal to 50%. That's right. Now, if the petal width is higher than 1.6, okay, this is 1.5, so 1.6 is this one. If petal width is more than 1.6, it goes this direction. When this direction says, it detects it's a Iris virginica, or else it will predict that it is not Iris virginica, it can be some other flowers. How is it? How do you feel this class today? Do you understand the whole concept I explained you today? Logistic regression is very, very, very important. Guys, trust me. Logistic regression is very important. Every day I used to take 40 minutes, but today I decided to take it long and finish the logistic regression completely. We have one more small thing left, softmax regression. That's actually not needed. That's not that important because as you covered lasso regression, ridge regression, and elastic net, the softmax is also same thing, but it is not that important at all. So I'm ignoring that. Are you all happy till this point, everyone? Did you understand what I tried to explain you? What is the important concepts? How we can visualize each of the important concepts? Kishore, how about you? Perfect. I saw your message now. Thanks. Okay, guys. Thank you for being with me today. I appreciate your commitment. It's really a it's really a good thing we completed the training models in 106 slides. When I look back at slides, I feel proud, man. Did I do this kind of good work all these days? Every day when I prepare slides, I really feel, oh my God, it's getting late. I need to wake up in the morning, again travel to office. But when I look back at the slides, I really feel proud. The great journey, man. Awesome slides, good stuff. Everything is so clean, neatly maintained, and you have represented everything properly. One more thing, I do not hesitate to tell you, I am also still learning machine learning data science. It is a continuous journey. You have to be little patient. We are not in a good shape yet in terms of proper hierarchy of training and technical assistance to all our guys. But I have a strong hope. We are 70% halfway through. We are forming a team. Things are going a bit slow. That's fine, but we'll reach there. I want support from all of you so that I can support you as well. Okay, I have 2 more minutes time left. Thank you so much. If you have any questions, please feel free to ask me. With this one, we have completed the training models clearly. Tomorrow, we'll be starting support vector machines. I'll try to finish the support vector machines by one more thing. This weekend, I'm not gonna keep any workshops. Enjoy with your family. Thank you for being with me all the workshops. So I don't want to bother you this weekend. Enjoy. However, I'll be uploading some videos. When you get some time, please watch those videos. And after completing the support vector machines, we'll get into TensorFlow. And with that, we'll finish the first batch. Okay. Thank you so much, guys. Thanks a lot for your time today. See you all tomorrow. Have a great day. Enjoy your work.